Yeah, thanks for having me. So I'm a teaching associate, and what I tell my student is the most important question is not how, the question is why. Why are you using this algorithm? Why are you making these adjustments? And I want to give some motivation why this is important. That's the first part of the talk. Then I go into Bayesian learning and try to justify that we actually should think simple. Machine learning algorithms are so complicated now that a human cannot actually understand why the machine has come to the result it actually says. And that makes it very hard to actually trust it if we cannot understand the result. And then I give neural networks as an example to show that actually you can keep them simple. And I want to say now that I will not arrive at a Bayesian neural network. I arrive at a combination which is different in this way. So motivation, that was in the news in February, that at the American Association for the Advancement of Science, there was a talk saying machine learning causing a science crisis. Problem is that scientists have so much data now that people just think, I throw it into a machine learning algorithm, I crank the handle, and out comes the right solution. So, but how do we know it's right? That's a big question. Another person of inspiration is Keith Baggerly. I think he's at the University of Illinois.
He's the speaker on, excuse me. He's the speaker on.
Okay, is that better?
No.
No? Okay, now better?
Is he on? I'm just asking if he's on.
It is definitely on. I just have to stop moving. Okay. I will try to stay fixed. Yes, he coined the expression forensic bioinformatics. And he feels also quite passionate about it. There are videos of his talks on YouTube if you want to see it. I had the opportunity to hear him when he spoke at the Crick Institute. He's quite inspirational. And the thing was, in 2006, a paper came out which said we can predict which chemotherapy is most suitable depending on the genomics of the patient, which had people really excited because chemotherapy is such that to kill the cancer, we nearly have to kill the patient. So to know something which will work best for that patient got people very excited. Clinical trials were started. He examined the paper and the data in it and said there's something wrong. I cannot reproduce it. So, and nobody listened to him, a bit upsetting. So he wrote to the editors. It was at Duke University. He tried to get somebody to listen to him. Then in 2010, something happened. And it wasn't that people suddenly started listening to him. It was that another mainstream news outlet had discovered that one of the main authors had lied on their CV. And they had claimed they got a prestigious prize, and they actually hadn't. And then people started, well, if he lies on his CV, should we perhaps start listening to Keith Baggerly? And the paper was retracted, the clinical trials were stopped. So it's just very sad that it took 4 years. He has further examples of that, and sometimes it is as simple as somebody slipping a line in an Excel spreadsheet, and the whole paper results are wrong. So we don't. So it is playing with people's lives because it is medicine. And since we are in medicine, so a little bit of more analysis behind it. If we have a test and we have a number of negative test people, so it could be a disease and they test negative, so they don't have it. And then we have a number of positive people. The true positive ones are the ones which test positive and are positive, and the true negatives are the ones the other way around. And then we have the false positives, which is not good because we don't really want to subject somebody to treatment for a disease they actually don't have. One of the examples is prostate cancer. There is a marker and you get a number, and on that number they might decide to operate on you. It's actually, the jury is out how much you should trust this marker. And if you're an educated patient, you might decide, actually, I'm not going to be operated on like my father did. So a lot of operations might be unnecessary. And we have the false negatives, which is also bad, because we don't want to miss somebody who has the disease and not give them treatment. So, and it's always written down in a confusion table, where I have the true values, N and P, negative and positive, and the outcome of the test. And ideally, we want zeros on the off-diagonal elements, off-diagonal. Okay, then this has been going on in medicine for a long time. So they created the phrase sensitivity, or true positive rate. That is the proportion of positive people we identify as positive, and the specificity is the true negative rate. It's also the rate where we get it right. And the complement to that is the false negative rate or miss rate, the ones we think they are negative, but we actually miss that they have the disease. And the other one is the false positive rate, also called fallout. Okay, yes, so quite simple. Then people, because in end effect, what the advice we give to doctors should be, if it's that value, you shall treat, or you should do something. If it's below that value, you shouldn't. So they want to make it very simple. So the next number they developed is the likelihood ratio for positive results. That means the likelihood is what is the probability that I get it right? And so there's the true positive rate is this likelihood, and I divide it by the false positive rate. That's the likelihood that I actually get it wrong. So, and I want that the top is large and the bottom is small. And we also have the likelihood ratio for negative results, which is exactly the other way around. It divides the false negative rate by the true negative rate. That one we want to have small. So, and then they give a nice little rule. If we would have a perfect test, it would be 100% sensitive and 100% specific, which means that my positive likelihood ratio will go to infinity because I divide by 0, and the negative likelihood ratio will go to 0. So, and in 2002 there was a paper which said that if the positive likelihood ratio is greater than 10 and the negative one is less than 0.1, we call the test meaningful, and the doctor should act on it. You can actually look these up online. There's the Cochrane Handbook of Diagnostic Tests, and you can be an educated patient and probably annoy your GP if you know these things. So medicine has quite stringent criteria because they know that our lives could depend on the advice they are given. And so, different case now. These are 2 newspaper articles from the US. In the US, they have a tool, it's called Compass, which predicts the risk of an offender to re-offend when they are released from prison. It just gives a risk score from many input data. And so the idea was, well, judges might be biased, probation officers might be biased. If we give it to a machine, we are not biased. So the organization ProPublica analyzed this algorithm. It's quite scary how much data they actually obtained about people. It seems privacy is not very important in the US, especially if you have offended. So they found 7,214 people who had offended. They could then, over history, whether they re-offended of these people, they obtained their risk score, so it was all publicly available, which is in itself scary. And they then just looked at who does actually re-offend and what was their score. So N means the people who didn't offend, and P are the people who did offend. So, and you can calculate the true positive rate and the true negative rate, which is already not that good. It's a little bit better than guessing. But if you calculate the positive likelihood ratio and the negative likelihood ratio, it's in a range where you wouldn't allow it as a medical test. You wouldn't say, you wouldn't say we act with a procedure on this test. But it seems it's okay if we just send people to prison. So that's the first bit they found out. Okay. ProPublica then split the data into black and white. Ethnicity is not part of the input because the idea was to make it non-biased. But if you calculate the false negative rate and the false positive rate for each of the groups, you discover that it gets it wrong. And it gets it wrong in a negative way for black people and in a positive way for white people. A black person is quite likely to be a false positive. So they will be predicted a high risk of reoffending, but they actually will not reoffend. While a white person is given quite a large false negative rate. So they are said that predicted they are low risk, but they actually then do reoffend. So the big question is, what has made the algorithm bias? Compass, the algorithm is not known, the company will not release it, so it's proprietary. The suspicion is that it's a neural network. But how do we know what made this bias in the neural network? If it has many layers, you cannot see where it made that decision. So these are some examples of where things go wrong and my motivation for this talk. And now, actually, to get more what I suggest as a solution. There are several challenges. We want to model the data, but we actually want the models to be simple, but still explain the data. It's a bit like Occam's razor. So if a simple explanation is sufficient, we are happy. We shouldn't make it more complicated. If you give a neural network many neurons, your model will be complicated because each neuron is essentially a dimension in the solution space. So you then have a very high dimension. So the next challenge is, what do we do when new data arrives? How are we actually confident in our predictions? And the last one is, well, how do I choose my model space to model my data? At the moment, there are lots of heuristic choices, and they work well. And I will give one example and say, well, actually, it might not be the wise choice. Okay. So I need to introduce a bit of terminology. So we want to predict data, and at the moment, just think of it like a continuous function. We want to predict, we have some points, and we just want to put a function through it. So I have measurements, T1 till TD, at some points or parameters. And these things I can measure with more or less effort. So the capital D is my dimension of the data space. I can make these measurements again and again. And the idea is that they are produced by an underlying process. So sometimes I know something about the process. It might just be physics. Sometimes I might know nothing. And that's the thing, there are unknowns. So if you have any measurement you do can depend on more parameters you cannot measure. In medicine, it might not be a good idea just to make a measurement to cut somebody open. So we cannot do some of the measurements, or it would be very costly. With oil companies, they don't explore deserts anymore, where it was very easy to drive in. They are now exploring jungles, and they are not allowed to build a road. So for them, another measurement is very expensive because they have to track the equipment on their back into the jungle where they want to do the measurements. So we cannot do this necessarily. If you know something about the underlying process, like the physics, then we would like to incorporate. And that's another example I give is we understand how sound waves propagate, but what we don't know is what material they propagate through. Seismic exploration sends sound waves into the earth and listens to the reflection. They know how the sound waves behave, but they don't know what they actually travel through, which rock they travel through, how the rock is stacked against each other. So that's what they have to guess somehow, sometimes with machine learning things. So that's the bit. There are lots of things we don't know. Okay. Now, the idea is that we choose a model space, and I describe it as candidate functions. I have these functions which actually obey the physical laws, I know. So that's good. They incorporate this. And I then say, well, my function which produces my data is just a linear combination of these candidate functions, or I call them dictionary, and that's why they are named D. So I just need to then find the coefficients, and then I say I'm hope. So I have building blocks from which I build my data, and capital M is the dimension of my model space. So I come originally from a numeric analysis background where we also try to find solutions. It's all algorithms. Machine learning are just slightly different algorithms. And the idea is often that your true solution lies in an infinite dimensional space or a very, very high dimensional space. And what you try to do in your algorithm is you just try to find a lower dimensional solution, which tries to get as close as possible to the true solution. Or I compared, we just walk around in a lower dimensional space. That is what the algorithm does. And with every step, it tries to get closer to the true solution. So that's the idea. Well, to make it machine learning, we actually introduce some probability, and we do that via the noise, because every measurement is in some way noisy. We cannot guarantee that it's perfect. And the idea is that the noise is normally distributed around 0 with noise variance sigma squared, which is a very strong assumption. So one problem with machine learning is that everybody assumes that, but is it actually valid? And it not necessarily is, because the normal distribution is not heavy-tailed, and a lot of natural processes have a heavy tail. So events at the end are more likely than the normal distribution predicts. But we carry on with that because we keep things simple. So my mathematical model is now my data is generated from the function, and I add some noise to it. If I now define a matrix which has the entrance, it's my functions evaluated at the points. It's called the design matrix. I can write it as a linear system of equations, which makes it a bit easier because we know how to solve those. We have done that for ages. So the main thing I want to draw attention to is that actually with what I'm proposing, this matrix D, the design matrix, can change dimensions. So it can change the number of rows, which is the number of data points I'm getting, measurements I'm getting. If I just get another measurement, I add another row. And it can also change the number of columns, which are the dimensions of my model space. So I start with a small dimension, and I start wandering around. And then I discover, actually, I need another dimension to get closer to my true solution. It can then create another column. Other thing to note is that there is a link. I said that the entries in the matrix are evaluations of functions, which is important to keep that in mind. Because if you have that link, you can evaluate it wherever you want. A lot of machine learning algorithms just specify the design matrix. And that means you're limiting yourself to point values. You cannot go away from it anymore and evaluate somewhere else. So ideally, you should keep that link going. Okay, so with sparse Bayesian learning, so for people who are not that mathematically inclined, I've made the change now so that you can just hold on to the blue writing and ignore the black writing. So the idea is that my coefficients in my model, which I need to find, are actually have a probability distribution. And the probability distribution, well, you probably know it has a variance, which controls the width of the probability distribution. But if you take the inverse of the variance, it's called precision. And if you have a large precision, so it means it's very precise, it's very peaked, like this. And I'm quite sure about my value of my coefficient. If it's low precision, then it's very wide, and actually the algorithm says, I don't know, which is better than it giving me a solution. So I prefer that I'm told I don't know than I'm getting a value which I'm supposed to trust. So I don't know is a good answer. Okay, then here's a bit more mathematics. If you have that assumption, you can have a prior distribution, And then the algorithm sees the data and it arrives at a posterior distribution for the coefficients. So, and we can calculate all that. So I'm not going into the details, how to get the formula. Just the nice thing is we can derive them and we can calculate them from the data. Okay. The way we actually get there is because we need to decide what is a good model. So the idea is that I have these parameters which control the width of my bit, of my probability distribution, and I now optimize with respect to these parameters. I want to find the best parameters so that my model explains the data, and that is called the likelihood. The likelihood is the probability of my data given my model I have so far. The term marginal here just means that I got rid of the coefficient c by integrating it out. And so there's the formula, how you get it, but the main thing is we maximize that now. So keep that in mind. Maximization is simple technique. If you take a derivative of a function, the derivative will always point in the direction, well, if it's positive, you will move towards the maximum. If it's negative, you actually move away from it. So that's the two possibilities. If it's 0, you are at the maximum with some precautions. And in this algorithm, you can find the derivative with respect to one precision parameter. And it's in the bottom line there. And the main thing I want to point out is that two of the, as I indicated, are positive. So, well, there's only one part with si minus qi squared. This bit we can calculate. If that is positive as well, then the derivative is always positive wherever I am. And that means actually my maximum is at infinity. It just keeps going upwards. If si minus qi squared is negative, then I can find a 0. Because at some point it will become positive if I vary my alphas, and I can find exactly the point alpha I for which it's 0. Or here are two pictures. So the first case, it goes to infinity, and we find the maximum there. And the second case is we can calculate a point where there is a maximum. Keep in mind that is the maximum for one precision parameter. All the other ones are fixed currently. So once I have found that one, then I look at the next building block and check what is the best parameter there. And it's an iterative algorithm because as soon as you change one parameter, the optimal value of the other parameters changes and it converges. And while it converges, many of the precision parameters will become infinite. And when they are infinite, they are actually the mean is 0. So, which means I actually don't need it. So that's the nice thing about this algorithm. It tells me which parts of my model space do I need to explain the data and which parts I don't need. So, or in other ways, we can remove it from the model. Okay. How do we know whether it's needed or not? For that, we need to know whether si minus qi squared is positive or negative. If it's positive, we know we don't need it. And interestingly enough, you can interpret these values intuitively. So there's lots of formulas, but the main part is in the middle where it says t minus d mu. D mu is the prediction of my data, because mu is the mean of the distribution of my coefficients, and I just have to multiply by the matrix D to get the distribution of my, I call them targets, of my measurements. So it's actually the quality parameter quantifies how well aligned my building block is with this error. If it's perfectly aligned, then I should just include it because it will help me removing this error. If it's vertical, then I should not include it because it will help me not at all. So this is the two extremes. So the QI tells me how good is it to have this building block or not. The other one, the SI, is the sparsity one. And you can also actually, so there's a lot of maths going on behind it, but if you think about it, you have one space is given by your current model, and you have a new building block, and you want to check whether that building block lies in your current space or actually sticks out of it. Think of it like the current space is the horizontal line here, and I can imagine another vector going out of this line, and I can measure how much it actually stands up against the other space by looking at the angle. And the angle is related to the parameter SI. So that's why there are sparsity and quality parameters. If my SI is very small, that means this building block is quite similar to the other ones. So I don't need it. It's actually not good for an algorithm to have similar building blocks because it becomes unstable. One building block can be exchanged for other building blocks. So it is important to try to keep these things separated. So, and yeah, okay. So, and that is now in one short bit the that Bayesian algorithm. It starts very simply. It initializes with a single building block, like Occam's razor. If I don't know anything about my data, I could just put one line through the average and so on. It is an approximation. And then I can say, check, is that good enough or is it not good enough? And if it's not good enough, I can get more building blocks and add them to my model. And the algorithm can do addition if my optimal precision parameter is finite, it adds it in with that optimal parameter. It can do deletion if it now happens that it discovers that actually I have changed all my other parameters and now this parameter will go to infinity. It will take the building block out again, which happens when there starts becoming dependent on each other, or you can re-estimate the optimal parameter. And that is essentially tries to address the first challenge, to build a simple model, and it becomes more complex as you get more data, as the data suggests that you need more things to explain the data. Okay, so this is a slide. It has the maths on, but the nice thing is you can predict, because I have the link that I have functions which I can evaluate. I can evaluate wherever I want. And if I evaluate it, I will get a probability distribution because the coefficients are probability distributions. And I can calculate the mean there and the variance. So if my variance is large, where I want to predict, the algorithm says, I don't know. If it is small, it says, I'm actually quite sure. There is a problem with that. And that's what I want to point out. Because it depends, crucially, on the values of my building blocks where I evaluate. So I have all these functions, d1 till tm, and I evaluate them at x star. If my function goes to 0 at x star, it will predict just 0. So the mean will become 0, and the variance will also become 0. So that is rather useless. But it does happen because this is a Gaussian function, and Gaussians are very popular because they are nice, they are one in the middle, and then they go to 0. And if you think, I call them bump functions, you can build any data with bump functions. You just add them together with the right coefficients. So, but it might not actually be the true solution to how the data was generated, especially if your width of your bump function is small. Then you just get lots of little bumps, but nothing to do with actually how the data was really done. So it's very important to think carefully how the model space is generated. So especially kernels are coming up and are more and more better understood. Okay, yes. But before I can and can explain how we solve this problem, that our predictions give us 0. I don't want my algorithm to tell me 0. I want my algorithm to tell me I don't know, if it doesn't know. I first need to actually show how we deal with new data. And it's very simple. You just put another line in your design matrix, and you can do all the calculations through their fast update formula. And you can calculate how much your likelihood changes. So that's the probability that your model, as we have it currently, generates that data. And it just compares my measurement, T star, to my predicted mean, M star. If that is 0, if I predict it perfectly, well, then the exponential of 0 is 1, and this is it could be positive. And I don't say that it will be positive, but the logarithm of 1 is 0. Anything which is larger than 1 will be positive then. So if you think about an exponential function which is quite peaked, if our prediction is good, it will be peaked, and so on. So that means in the middle, it will be beyond 1. And the change in our likelihood, or the logarithm of the likelihood to be precise, will be positive. And it means the new data affirms the model. Or it could be negative. That means the model is not good enough for that data, so I need to do something. I need to perhaps change the model space or let the algorithm adjust all the precision parameters so that it is also good for this new data point. But that's the second challenge. It essentially says that my model can update itself if new data arrives. And with satellite data, because we are getting lots from the Sentinel satellites, you could, for example, the satellite can carry a model of what it expects to see on it computationally. If it's a sparse model, you don't need much. And when new data arrives, it can just compare it. Does this data fit into my model? If yes, it says, well, actually, I don't have to transmit everything to Earth. Downlink, that's one of the big problems. To get all the data down, it does. Or it says, well, actually, what I see now doesn't fit at all in my model. I need to alert somebody on the ground. Wildfire detection is an example that it would say anomaly. And then a human would look at the pictures and say, well, actually, there is a fire. So it makes it computational more feasible to have a sparse model it can carry with itself. Okay, that's the second challenge. The third challenge is, how can I actually have confidence in my predictions? And that's quite a bit difficult. So, because most algorithms will at most give you like a probability of confidence. And this is a different suggestion I have. So, we have a predicted distribution at a new point x star. So we have that from our evaluation of our building blocks at x star, but we can also estimate the distribution, and it's a very simple idea. We just calculate the mean of all the data we have. So we don't have t star, we just want to predict at x star, and we calculate the variance of all the data. So, or you could take a subset if you want to, like a neighborhood. And then we can calculate the expected change in likelihood. So it's the expectation with regards to the to the estimated distribution. And it's again the logarithm, because that's easier to calculate, because logarithm and exponential change. And again, it compares my predicted mean to my estimated mean, and then compares it to the predicted variance. Because if I'm within variance, it says, well, that's fine. I think what I'm off is caused by noise. So if I'm very wrong, for example, if my M star is 0, then I will actually get a negative expected change, which means my model cannot do anything there. It's an indication that more data needs to be gathered. So companies are quite keen now, because data gathering can be very expensive if they know where they have to gather the data. So that's one bit. So you have then a candidate area where you can tell them, look for data there. If it's positive, the expected change, then we say we are fairly confident in our predictions, even though these numbers, they are not absolute numbers. So that's one thing I have to say. They are not probabilities or anything. It's an indication. So more work needs to go there. But it is something, and that's the third challenge. So now an example, because that might help. So there's the Lena picture, because everybody uses it, and I threw away 45% of the pixels. And I then made it hard for the algorithm, because I chose quite an unsuitable model space. And my model space are just the Haar wavelets of size 2 by 2. And they are 2 by 2 pixel blocks, which the first one is just a uniform color. The second and third one are horizontal line and vertical line. And the last one is a checkboard. And you could build any pixel combination out of these ones. They are the building blocks. So if I start using that one, I can rebuild it, but the main thing is there are lots of black dots, and there are 2 by 2 blocks where there was no data. If there's no data at all, the algorithm says I have no idea what I should put there, so it just puts a 0 there. And I made it hard. So the second picture is the scaled absolute difference between what I'm predicting and what the true pixel values are. And of course, it picks up the black dots where we have missing. Equally, the scaled expected change in likelihood, if you wanted. The main point is there is a 0. So where it's 0, and it just stayed the same. If it's positive, it actually thinks, oh, I'm doing well in this area. If it's negative, it says, well, that is not good. And I've scaled it so that it's between -1 and 1, because you can get very different values depending on the data, just to make it more displayable. So once we have that, we can then do strategies how to improve it. So I should say this FSIM, that is called the Feature Similarity Index. And because humans are actually not that bothered about slight pixel changes. So to base your quality measure of your reconstruction on pixel values is not good, because humans are good at interpreting. What humans do not like is if you don't have lines anymore, so if the structure in the image is missing. And FSIM is a measure which tries to quantify this. And the closer to 1 it is, the better. The happier the humans are to look at that construction, you could say, reconstruction. So the first part, I've just added 5% more samples, and I've added them where my expected change in likelihood said that is where you need more data. And I get my FSIM up to 0.93, so that's better. Or I can actually choose a different model space. And so it's up to the decision. It's still not looking good, but it is better. It doesn't have holes anymore. Okay. Then, yeah, last part. Okay. Oh, I have to speed up. So neural networks, and they are overly complicated, and I want to make the case here that you can get away with things. So the MNIST data set of handwritten digits is 28 by 28 pixels with a digit in it. So the model space, not the model space, the data space has dimension 784. Don't think of it as images, think about it as points in a very high dimensional space. So, but I want to distinguish the digits. So let's start simply. I have only 0 and 1. How many dimensions do you think you need to distinguish them? Guess? Over 500? Nobody? Under 10? nobody either, between 10 and 500. So that's probably then. Actually, yeah, I use an autoencoder. Autoencoder are neural networks. It's very simple, just 2 layers of synapses, and you have one set of hidden neurons in the middle. It encodes from the input to the hidden set, and then decodes from the hidden set to the output. And the challenge is just to put, the input has to look like the output. And if you see these neurons with 1 in it, they are for the bias. The bias is just the average of your data. If you've moved your data so that the average is 0, you actually don't need a bias. But people really underestimate the bias because it can actually really influence your predictions, and you have to be aware of it, that it does things. And I hope in the illustration it will show it. So very simple autoencoder, and you only need 2 neurons in the middle. So you can, with 2 digits, you can get away with 2 neurons. So the first image is what my encoder gives back. When I put my data in, my 2 neurons in the middle give me 2 numbers, and I can plot them in a 2-dimensional plane, and that's what it is. And I colored the ones green and the zeros red. And you can see that it separates. What actually the algorithm has done is, in this 784-dimensional space, it has found 2 dimensions along which, when you look along those, you can separate the data. So the second picture is what happens when within a neuron is the activation function. Here it's the logistic sigmoid, which will map large numbers to 1 and small numbers to 0, and so on. You can think of it like a probability, and so on. But if you think about it in a space, it just pulls the data apart more, and so that you can have more chance to separate it. So that's all what happens. And oh yeah, I need to go back to this one. So remember that we had our building blocks. The neural network generates the building blocks for you. If you look at like the neuron with number set 1, it has D lines coming out. Oh, yes. And these D lines you can rearrange into an image, and that's the building block. Because the output is just these building blocks multiplied by the number which is stored in the neurons and added together. It's a linear combination. And these ones are there's the bias right at the end, so I say don't underestimate it. It looks like a 0, and the other 2 bases look like a 1 and a slanted 1. And then you can carry on. You can, yeah, that's the reconstructions. Beautiful thing about autoencoders is because the output shall look like the input, it becomes human interpretable and so on, because it tries to reproduce it in a way humans understand. While with other techniques, you get the same space, like principal components will give you the same space, but those vectors you will not understand. You can do it with 3, and so on. There's this one. Middle one might look like a 2. So you can do it with 10, but then it's very hard to illustrate it. But again, the neurons fire for certain digits, and that's the last little square I have there. It just colors in for which neurons it fires, and that is the parts just in a table, which neurons fire for which digits. If you look at like neuron number 10, it will fire for 7 and 9. And it's quite interesting because you would think 7 and 9 look similar, but so people write the 9, and some people, when they write the 7, they put a tick at the front. And if you consider the tick, that is what makes it similar to 9, and that's why they were grouped together in one neuron. So, and you can even see that here, that these are the 10th neuron and the 7th neuron look like a 9 and a 7. So they both try to cater for these digits. And the bias just becomes a white plop because it is the average of the data. And they are all, so reconstruction is not good because you can't do it with 10. There's too much, like the little tick on the 7. If you need to do more detailed distinction, you need more layers. So, because you would need another layer which distinguishes within the group of 7 and 9s, the 7 and 9. So, but you can just add more in. And there's the whole idea why it's work in process. So I want to combine the two. The middle layer in my autoencoder, I replace by the Bayesian learning, which can change in dimensions. So what that means is the middle part can introduce more neurons. So you can start off with 2 neurons, and when you introduce another digit and it says, actually, I can't do it anymore, it can then create another neuron. And because we know with the quality and sparsity factor where we need to put it to get the biggest effect, so it can interplay, it can start learning the model space from one bit to the next one. Okay, yeah, and there's my conclusions. It's flexible, it tries to adjust itself for new data, it can say something about the confidence and also where we should gather more data. Yeah, and I think that's just, if somebody wants to contact me, the easiest way is via LinkedIn. Yeah. Okay, thank you. So.
So you mentioned at one point that you use these Gaussian bump functions as basis functions. Wouldn't that make like the model prone to overfitting?
Yes, that's why I advise not to do it. So if they were an example, don't do it. The ideal bit is actually if you combine, you have to go into quite mathematical theory, what functions to use, but if you combine these kind of functions which depend on the radius, on the distance between different points, to combine them with a low-order polynomial, then things will work out well. So.
Then you have some global information involved and not just local.
Exactly. That's,
yeah, that makes sense.
That's the idea. Or you can, the whole theory of kernels is you can build kernels out of other kernels. You can multiply them together. So the possibilities are endless, but as I said, the important question is why. Why do we build the kernels like this? So, and that's a bit of an open question, really. Okay. Yes. Yes.
How do you deal with or decide on biases when you have a large number of sort of hidden layers?
Well, the biases get weighted by the neural network. So the neural network will calculate them. So I went to a talk where somebody's introduced the phenomenon which people now discover. They have the neural network trained on a certain set of images which it can distinguish, and it gets it right so many percentage of time. And then what people discovered is if you feed in a completely different set of images with different categories in, it actually, the neural network is better on the set of images it has not been trained on. And the reason why it is because of the bias. If the second set is similar to the bias of the first set, it will do better, because it will always try to use that to predict and reconstruct the other images. So you shouldn't underestimate it. Yes. Okay, any more questions? Yeah. That's a bit like the plaque art. So I mentioned the seismic explorations, and people can quite well simulate. If they say what the structure is under Earth, they can simulate perfectly the reflections they will get. So there the idea would be to have these simulations as the building blocks, and scale them, make them bigger, make them smaller, and then just add them together and see whether we can come up with what we actually did measure. So, yeah.